Hello, everyone. Good morning. I hope all of you are doing very well. So this week, the last week of the semester, we will do the Ito isometry and the multiple Wiener-Ito integral. Okay, so this is section 5.5. The Ito isometry. In the Ito theory, of stochastic integration, we have the following equality. So suppose f t is an adapted stochastic process, and we integrate from a to b of ft dbt. This is the Ito integral. And then we take square, and then we take expectation. The equality say that the left-hand side, maybe I write it here, equals to expectation of the integral from a to b of ft absolute value square, and then dt. Note that here is dbt, here is dt. And this is true for all f belonging to the notation that we used before, adaptive stochastic processes in the L2 space of omega times the interval from A to B. So we have this equality. That we have the Ito isometry from this space L2 sub-adaptive stochastic processes omega times AB to the L2 space of the probability space omega. And this correspondence, or this mapping, is from F to the integral from A to B of ft dbt. So this is the Ito's isometry. And now I'm adjusting the position. Yeah. Okay, now the question. What is the generalization of this isometry to our new theory. To our new theory of stochastic integration. Okay, first let's do some examples. To get a concrete feeling okay. To get a concrete feeling of this of some, a concrete feeling of what we can get. Okay, so we go to the next page. Positioning this page. Okay, good. This is page 58. Okay, so example 1. Well, the example 1 is the simplest one that we have been dealing with. The integral from 0 to t of b1 dbs. We know that this equals to b1 bt minus t. Okay, so 1. The integral from 0 to t of b1 dbs square. We want to find out the expectation of the square. And this is expectation of b1 bt minus t square. And this equals to, I would like to ask you to check. You check. Equals to t plus t squared. It's not very hard to check, but it is harder than 2. On the other hand, the integrand is b1. And if we square it, and then take the expectation, and integrate from 0 to t, and then dt, I'm sorry, this is ds. Namely, this quantity is the right-hand side. The right-hand side here, this integrand square, and then expectation integral AB. So it is this. And it's very easy to see this is very, the expectation of B1 squared is 1 ds. And so this equal to T. So 2 is much easier to get than 1. Now compare these two, this quantity and this quantity. We have T plus T squared here, we have T. And so we have the expectation of the square of the integral from 0 to t, b1 dbs square. This being equal to t plus t square is certainly greater than or equal to t, the integral from 0 to t, of expectation b1 square ds. So this inequality is greater than or equal to. But when we want to extend something by continuity, the inequality we need is the reverse of this inequality. So, but we need the following inequality. For the generalization by continuity. Namely, what we need is this inequality. Square the expectation is less than or equal to something here. Expectation of the integral from 0 to t of b1 square ds plus something here, which we need to find out. And so later on we will address this issue. Okay, so let's go to the next page. Okay, this is page 59. So this is example 2. Example 2 is the integral from 0 to t of b1 minus bs dbs. This equals b1 bt minus 1/2 bt squared minus 1/2 t is from section 5.1, page 35. And we have 1. The expectation of the integral from 0 to t, b1 b1 minus bs. This stochastic integral square, this equals to, use this to here, and you can compute that equal to t minus 1/2 t squared. This you check. You check this equality. Now this time, comparing with example 1, this time this equality is much harder to compute. And it takes time, so I want you to do it. It is a good exercise. On the other hand, let's compute the right-hand side of the isometry. The expectation of the integral from 0 to t of the integrand square, and then ds. This is ds here. What is this? This is the integral from 0 to t. Bring the expectation inside. And that is integral from 0 to t. Now, b1 minus bs is normally distributed with mean 0 and the variant 1 minus t. So this is 1 minus, 1 minus s, ds. And this, you compute it, is t minus 1/2 t squared. So we have the same thing here. Therefore, we have the expectation of the integral from 0 to t of b1 minus bs dvs. This new stochastic integral square and then take expectation equals to the integral from 0 to t of expectation b1 minus bs square. ds. Now this expectation here, you see we can bring it inside the integral or we can bring it outside. It doesn't matter by the Fubini theorem. Therefore, we have this, that we have an isometry. Okay, I think this video is too long. It takes really a long time to upload the video, so we stop here and we'll continue in the next video.